Working our way through chapter 5 here. This is section 5.5. We're going to look at derivatives of bases other than e. And we'll do a little bit of review of just what e, the derivative of e to the u was, and then we'll talk about what if that base got changed. So the definition of an exponential function to a base a is kind of shown here as a of x is equal to e to the natural log a multiplied by x. We know that this kind of ends up washing away, and I would get that this is a raised to the x. Okay, so if a equals 1, then y equals 1 to the x is equal to 1 is a constant function. Yeah, we know that. Whoopsie, too far. A few things to review again. Just some exponent laws. And a to the 0 we know equals 1. A to the x times a to the y. If I have two bases that are being multiplied, I add their exponents. If I have the quotient rule, a to the x over a to the y, I subtract their exponents. And if I have a power raised to a power, I multiply the exponents. So we multiply. So remember those, because those are going to be helpful. Just a little bit of a good old review from advanced algebra, maybe pre-calc, solving for x. You know what I like to do on these? There are various methods, but I know the value of 32. I know my 2's, I know my 3's. 2 to the first, 2 to the second. Do you know these? I hope so, because what it helps is if you have an inkling of some of these numbers, that they're special numbers, you can make light work of some things. So there's my 2's. 32 I can restate as 2 to the 5th. Now, since I have bases that are the same, the exponents must be equal, correct? And then I get x equals 8. Solving that, x equals 8. Do you know your powers of 3? I think it's important to know these. Probably most of us know them up to at least 3 to the 3rd, but I'm going to suggest it would be valuable to maybe even know them a little beyond that, 27, and then the next one's 81, and 3 to the 5th, we'd get 243. You know, so that recognition of these numbers is important, because you can break them down then so quickly. 27, do you know what it is? Well, it is a power with a base 3, 3 to the 3rd. We could extract our exponents and say, well, if the bases are the same and we have an equality statement, then the exponents had to have been the same. 2x equals 4, x would be 2. Okay, this one's a little bit trickier because 8 squared, not 8 squared, is it? 8 squared doesn't give you 16, 8 squared gives you 64, so it's not powers of 8. However, 8 I know as 2 to the 3rd. And 16, we just talked about it, 2 to the 4th. What do I do with this? Well, power to power, 3x minus 9, I can multiply, can't I? So I'm distributing as I multiply that through. That means these exponents must be equal. And we get to, let's subtract a 3x, bringing it over. Give me a 1, subtract an 8. Looks like, what's 1? 1x is equal to negative 17. X is negative 17. Beautiful. 1 over 27, we can rewrite that. Ooh, 9 we can rewrite too. 3 squared, 2x minus 1. 27, it's 1 over, so that's 3 to a negative 3 raised to an x minus 3, power to power. Multiply power to powers, because they're so powerful. And we're sitting with that. Add this over 7x, add this over 11, divide by 7, 11 sevenths. So just a nice quick review on dealing with equations with exponents. Log equations. What you're going to notice here, we have some log equations with bases that aren't e anymore. We've done e's earlier. This is a base 4, right? Base is 4. And remember the little pattern, 4 raised to this power will give me that number. 4 raised to x gives me 1024. And you know, I think 1024 is a value of 4. It might, oh man, I'm sorry, I'm kind of lost on that one. I think it's 5. Yeah, it's got to be 5. So, oh, well then x turns out to be 5. The other thing you could do if you had a calculator, you know you can do your change of base on your calculator as well. On the TI-84s at least, if you go alpha and hit that, what is it, the window button, which is F2, you're going to pick up a log where you can insert your own base and your own value, your own argument there, and you would find out it's 5. All right, 27, not 2 to the 7th, 27 raised to the x gives me 3. Well, 27 is 3 to the 3rd raised to the x, that's 3 times x, gives me 3. That's like a 1 over there. 3x equals 1. Exponents must equal on this scenario. X equals 1/3. 9 to x equals 1. 9 to the x equals 1. Okay, 9 to the 0 equals 1. The value of x in this case is 0. Square root to this gives me that. Square root of 2 raised to the x equals 16. 16 is a 2 to the 4th, isn't it? 2 to the 1/2, because the square root, multiplied by x. Compare our exponents for the equality statement, and x would equal 8. That's a quick review, you guys. Now, definition of a log with a different base. We used to need to really have a reason to do change of base formula because our calculators typically wouldn't handle a log of base 2 of 16 for us. It didn't know how to do those. But we could transfer it and change it into a natural log of x over a natural log of a. I always kind of thought of it as this. This is higher than this, so this was always on top and this was always producing the bottom. X was a higher value. It's above the a, isn't it? So change of base formula was pretty easy to remember. Natural log of x over natural log of a. And for this example, you know, I could have went natural log of 16 over a natural log of 2, but calculator-wise I could do it. But the other cool thing is you could do whatever base you wanted. And so I could take and move it into a convenient base. 2 to the 1st gives me 2. 2 to the 4th gives me 16. My answer is 4. All right, getting into the derivatives. Get to the calculus. Woo! We're 8 minutes into this video and we're now talking calculus. Excellent. So, derivatives of bases other than e. What do you know about e? Well, we had already studied derivative of e to the u is. It is itself times the chain rule u prime. Keep that in mind because you're going to see some similarities here. But that was with a base of e. Gives us all that. Now, what would happen if maybe I have the derivative of 7 to the x? How would I do that? Well, here's the formulas for it. It says natural log of a. We have a little of adjusting factor here. Natural log of a and then a to the x. And it is itself there, isn't it? Now this is with a nice clean exponent where it's just x. And if I took and thought of chain rule, derivative of x just produces 1. So that's why you aren't seeing it there, because if I've just got a base to a single x, the chain rule is going to result in 1. What if we had something a little bit more, maybe 7 raised to the 2x? Now we got chain rule. So we got the natural log of the base times the power itself there, and then du over dx. If you'd rather say this as u prime, that's fine. So I could say it's natural log of a times a to the u, it is itself, and then u prime. All right, what about logs? What if the logs are no longer an e? So we knew natural log of x, its derivative was 1 over x. Or natural log of u, it was u prime over u. Really, it was 1 over u, wasn't it, times chain rule. And we got to kind of memorize it. We just memorized it as u prime over u. So now what if the base is not e like it was in natural log? What if it's a? Well, it becomes 1 over natural log of a, and then times x. So quite similar, 1 over x, I just have this extra factor of the natural log a, like we had an extra factor of natural log a when we were doing the exponentials. What if our x is a little bit more than just x and maybe it's some function u? Well, we're still going to get 1 over natural log of a and 1 over u. So we have natural log of 1 over a, 1 over u, and then times du dx, which is like a u prime. And that is super messy. So let's rewrite this. We'd have 1 over natural log of a times 1 over u times u prime, or u prime over u natural log a. Another way to see it. Practice a few. Okay, base is 3. This is the format that's going to go, how do I want to write this? A to the u, its derivative is natural log of a times a to the u times u prime. That's our pattern we got to follow. So y prime equals natural log of the base, natural log of 3, times a to the u. Well, a to the u is 3x times the derivative of x, but that's just 1. So we end up with y prime equals natural log of 3. You know what? I'm going to rewrite that as 3 to the x natural log 3. Then I don't need to use parentheses. Base is 4. So we're still in this pattern. Y prime equals natural log of 4 times a to the u, 4 to the 3x, times the chain rule, the derivative of the exponent, which is a 3. Not really any great way to write this. You're going to need to use some parentheses. Maybe something like that. All right, let's try another. 5 to the x squared. So remember, it's natural log of the base, a to the u prime. That gets us our derivative. Y prime equals natural log of 5. Got the base. Times itself, 5 to the x squared, times derivative of the exponent, 2x. Not any great way to write that. I'm going to need parentheses no matter which, how I arrange the multiplication. Let's see, this looks like a 3 minus x squared, doesn't it? Okay, so our base is 5. Y prime equals, well, we've got a natural log of 5 to account for. We have the expression itself, and then we have the derivative of the exponent, which would be 0 minus 2x. So just a negative 2x, it looks like. Okay, I don't want this to look like subtraction, so I'm going to bring my negative way out front, negative 2x natural log 5 times 5 to the 3 minus x squared. They're pretty easy patterns. Takes a little bit of memorizing, of course, but that's how to do them. And then finally we get into the log ones. Find the derivative of each. All right. The base is not e. So now I've got to remember what this pattern was. So if I have the log of with a base of a to the u, or of u, it's going to be the derivative will end up being 1 over natural log of a times 1 over u times u prime. So we're going to have y prime equals 1 over natural log of a, but our a is 5, times 1 over the argument there, 1 over x, times the derivative of x, which is going to turn out to be 1 for us, which we don't even have to write, do we? So we could say that this is 1 over x natural log 5. There's our answer. Log with a base of 3, and here is the argument inside. So this is like our u, isn't it? So we're going to have y prime equals 1 over natural log of the base, which is 3, 1 over u, which is the sine x, and then the derivative of sine is cosine x. Okay, cosine x over sine x is cotangent x divided by natural log 3. Y prime equals, there's our answer. Let's do this one. Oh, this one's tricky. Understood base of 10, right? Log without anything written is a base of 10. So this goes into a y prime. 1 over natural log of a, which is 10. 1 over u, this is all our u, x plus 3 to the x. And then times the derivative of the u, so this will become 1 plus, oh, derivative with a different base. It just keeps getting more interesting, doesn't it? This is what we did on the prior problems. So adjust the base, natural log of 3, multiplied by itself, 3 to the x. Derivative of x is 1. Whew. There's not a lot to do, you guys, on this problem as far as condensing. We could call it 1 plus 3 to the x natural log 3. There's the numerator portion. And the denominator, we could have x plus 3 to the x multiplied by natural log 10. What a problem. That's quite a derivative. All right, the next one, D. We're going to make use of some log properties to help us out on this one. So, log properties are going to come into play, because that might make taking the derivative just a titch easier. Log, we see we've got a base of 2. This 2x plus 1 that's cube rooted could be written as a 1/3 power. And the log property with a power means, where's it coming to? All the way to the front. Chugga chugga choo choo. So the caboose can come forward as 1/3 log base 2, 2x plus 1. Now we can go into the whole 1 over natural log a, 1 over u, u prime. Okay, so I'm going to get y prime equals, the 1/3 is going to be permanent, it's out front. Natural log of the base, 1 over natural log 2. I think if you think of it in series of steps here, 1 over u, this is our u, so 2x plus 1. Now the derivative of u is going to be a 2. Simplify, so y prime equals. That 2 is a multiplier. Bring it all the way out front, 2/3. You know, okay, so how do I want to write this? I'm getting all kinds of extra marks. 2 over 3, there's my 2/3. The rest of this stuff is in the denominator, isn't it? 2x plus 1, natural log 2. Why not call this 2 over 6x plus 3, natural log 2? Look good? I think so. Find an equation of the tangent line of f of x equals 6 to the x where x equals 2. Equation of tangent line, that's something we've been doing since like early chapter 2, long time ago. But we know in order to get a tangent line we need f prime of x. We actually need f prime of 2 to get the slope at 2, don't we? So f prime of x, well, our function is 6 to the x. So the derivative is going to be natural log 6 and then multiplied by 6 to the x. Derivative of x is 1. So there's our derivative. Now, remember it was a up, natural log of a times a to the u times u prime. That's the derivative of a to the u. Okay, so that's all I did for getting that. Plug in 2, we're going to get natural log of 2 times 6 squared. We could call that 36 natural log 2. All right, let's see, where x is 2. I need a point, don't I? In order to write the equation of the tangent line, I need a slope, which I got. We have the slope at 2. Now we just need the point. 2 comma what? Well, back to the original function. To find a y value, we go back to the original function, f of x, 6x. F of 2 means 6 squared. That comes out as 36. We just solved the mystery. The mystery is 2 comma 36. We have a point. We have a slope. We can write the equation of a tangent line. Y minus 36 equals the slope, 36 natural log 2 times x minus 2. Quite lovely. All right. W is find the weight of the culture after. Well, this is going to be just W of 0. Don't know why it's starting to do that. And then just plug in your 0. 1.3 over 1 plus 0.3 e to the negative 0.40 goes in for our t. Well, this goes to 0. E to the 0 goes to 1. And we're left with 1.3 over 1.3. Looks like 1 to me. And then you can do for the other hours as indicated. All right. Here's the homework. Enjoy.